Okay, so we're covering a problem from Calculus 1 in optimization that a student shared with me. So the idea behind this problem is that you have a metal sheet, and we're going to be looking at a cross section of it and bending up its sides to try to maximize the amount of water it can hold. So the question basically boils down to what angle theta can we choose so that the area of this trapezoid is as large as possible. That's what the problem is. One thing you might be a little bit confused by is, although the question is asking about maximizing the volume, because the length is something that we don't really control in this problem, we can just take a look at the cross section uh, of the object. Right, that's what we're looking at here. And if we maximize the cross sectional area, that's going to maximize the volume overall. So this is actually really just a 2D problem. Okay, so I hope that if we break this problem down into components, it'll hopefully seem a little bit easier. But what's given to us is that each of these is going to be 15. And the idea is that if we have a really, let me write it this way. If we have a really steep theta and they're totally vertical, well, in this case, the height is going to be really large. So it's going to be a thin container, but a really tall one. Whereas if we made theta really small, then the container will be very wide, but very shallow. So it's sort of trying to figure out what compromise is going to give us the most water. And, well, the way we break this down is just to make theta a variable and just write our expression for the area of the trapezoid. So the area of the trapezoid is going to be the sum of, let's say, these components, and I can define like a temporary variable called h. So the area of the middle component, the rectangle, is going to be 15 times h. And then, oops, let me just make my handwriting a little bit nicer. So that's 15. And then the area of each of the little triangles, and keep in mind that there's two of them, is going to be, let's call this base, let's call that height, right? 1/2 base times height. So let me just quickly go through and figure out how to write h and b in terms of theta. So base is just going to look like 15 cosine theta. Whereas h is going to look like, well, I think it's just 15 sine theta, right? This is just regular trigonometry. If this isn't clear to you, then go revisit some SOHCAHTOA rules and your basic trigonometry. But once you get to this point, you can imagine just plugging in for the value of h here, for the value of b here, and the value of h here. And you should be able to express area as a function of theta. Right? It's going to, you know what, I'm going to leave the rest of the problem to you, but you should be able to express area as a function of theta, and you should be able to take the derivative. So area is a function of theta is blah, blah, blah. And then you should be able to take the derivative with respect to theta. So I'm going to call that a prime, right? And that's going to be equal to blah, blah, blah. And to optimize this, you're going to set it to equal to 0, and then try to find the value of theta that solves this equation. And then you have to go through and do your due diligence and check that, in fact, it's actually a maximum, and also compare it to the boundary values of theta, right? Your due diligence is, you have to also compare it to the case when theta is equal to, you have to figure out what the area is when theta is equal to 0 and 90 degrees, just for sake of crossing your dotting your I's and crossing your T's. But I'm going to guess that this is not a trick problem, and that the value of theta that solves this equation is probably going to be your maximum. So yeah, that's a pretty short video. You know what? I'll give you just a tiny bit more hints, right? So if area of theta looks like some term some constant times sine plus some other constants times sine cosine, right? This should be pretty straightforward. The sine piece should be pretty straightforward. That's just one of your most fundamental derivatives. But the sine theta, cosine theta is a tad bit trickier. And when trying to find a prime, the derivative, you can just charge ahead and apply a product rule if you want. But a nice little trick is to remember that sine of 2 theta is equal to 2 sine theta cos theta. And the idea here is that if you see a sine theta cos theta, you can convert that into a sine 2 theta. Well, I guess you should call it sine 2 theta over 2. Because it's a little bit easier to think about taking the derivative of this one on the left-hand side rather than the right-hand side. But however you want to do the derivatives is up to you. Just go through, check your work carefully, check your derivatives carefully, and go ahead and solve that out. All right.